Good morning, everybody, and welcome back to second semester of AP Calc. We are going to be focusing on integration this semester, and integration is the process opposite of differentiation. So we need to really look at the basics first before we start to look at the more complicated. Now, as you should remember, when we first introduced differentiation, we introduced finding the derivative of a polynomial. And we're going to do the same thing today. We're going to first look at integrating polynomial type functions. So let's first remind ourselves, if you had to explain to someone how to find the derivative of a polynomial type function, what would you say? How would you explain it? Well, typically what we would say is the first thing we would do is we would multiply the exponent by the coefficient of each term. And then once you did that, you would subtract 1 from the power of each term. And that was basic differentiation. So because integration is exactly the opposite of differentiation, we're going to do the opposite operations in reverse order. So the first thing we're going to do in order to integrate or to find the antiderivative is we're going to add 1 to each power of each term. And then we're going to divide the exponent, divide the coefficient of each term by the new power. So instead of multiply, subtract, as what we did with differentiation, we add and then divide. All right. Now, the symbol used to denote the antiderivative or differentiation is this sigma symbol. Okay. That tells us that you're finding the antiderivative of the first derivative. All right. So we're finding the antiderivative of a function, which means that you're finding f of x. Okay, you're finding the original function. All right, so if you look at it, all right, one of the reasons we don't write it as such is that a problem will exist. Okay, and the problem is that although the antiderivative of f of x d of x should be f of x, there is no way of knowing if the original function had a constant term or not. And that's because, remember, the derivative of a constant is 0. So, because of that, we need to recognize that when you're taking the antiderivative of the first derivative, it equals the original function plus c. Okay? And c represents an unknown constant. And what's important here, and I cannot emphasize this enough, in the number one place people lose points on the AP exam, all right, is that C must always be added. Now, as we work further along finding antiderivatives, we'll talk about how to identify C. But there's really only certain circumstances where that constant can be identified. All right, so let's look at some examples of doing this method, where we add 1 to each power of each term, and then we divide the coefficient of each term by the new power. So if we look at this first polynomial, all right, the first question you're always going to ask when doing these, step 1, is it a polynomial? Now here, okay, when we look at this first example, it sure is. It is absolutely just a polynomial. All right, so then what we're going to do is for each power, we're going to add 1. All right, and we get 3x to the third plus 2x squared plus 3x to the first. And then you're going to divide every coefficient by the new power. And your antiderivative is going to equal x to the third plus x squared plus 3x plus c. And you need to include that c. Now remember, you can always check your work. You can find the derivative of this answer and see if it equals the antiderivative, which in this case it does. All right, let's look at our second example. All right, if we look at this second example, it currently isn't a polynomial, it's a rational function. So we have to convert it to a polynomial. Now in this case, we can do so by separating each term in the numerator over the denominator. And we end up getting the antiderivative of x squared plus 2 minus 4x to the negative 1 dx. Okay? So now we can do what we did before. We're going to add 1 to every power. Okay? And we get x to the third plus 2x minus 4. All right? And then we're going to ask ourselves, all right, we're going to divide every coefficient by the new power. All right? And we are going to get 1/3 x to the third plus 2x plus c. Okay? Now, if we do it this way, we've got a little bit of an issue. Because if I were to check my work here, I get x squared plus 2, and that's it. We'd be missing this term. And so what's important to know is that, okay, if you are ever asked to take the antiderivative of x to the negative 1, that equals the natural log of x. All right? So this is actually not true. And either is this. And either is this. What this actually becomes is 4 ln x. 4 ln x. And so our final answer would be 1/3 x to the third plus 2x minus 4 ln x plus c. Okay? This is one of the special antiderivative properties. Okay? One of the special antiderivative properties. All right. Now, I would like you to do the next two on your own. So, the next thing we need to look at is when basic trig functions are involved. We learned that the derivative of sine x equals cosine x, and the derivative of cosine x equals negative sine x. Similarly, we just need to memorize and know what the antiderivatives equal. The antiderivative of cosine x dx is sine x plus c, and the antiderivative of sine x dx is negative cosine x plus c. All right, so let's use these to find the antiderivative of the following functions. So what is the antiderivative of 2 sine x plus cosine x? Well, the antiderivative is going to be negative 2 cosine x plus sine x plus c. And we only have to include one c. All right, if we were to look at the next example, what is the antiderivative of t squared minus sine t dt? Well, it's in polynomial form. We're going to add 1 to our power and then divide the coefficient by the new power. And then with negative sine t, we're going to make it cosine t. And we get 1/3 t to the third plus cosine t plus c. Go ahead and do the next two examples on your own. Alrighty, so let's look at how else you're going to be asked to find and use antiderivatives. And here is an example of such. Use the given information about the first derivative and the second derivative to find f of x. All right, so we know that the second derivative of f of x equals 2. The first derivative of 2 equals 5. And f of 2 equals 10. So we're going backwards, and we're going to have to go from the second derivative to the original function. Well, we know that the antiderivative of the second derivative is going to equal the first derivative plus c. Okay? And because we know the second derivative is just equal to 2, all right, if we take the integral of that and find the antiderivative, we know it's going to be 2x plus c. Okay? Well, this c gives us a slight issue. But, all right, we know this equals the first derivative. All right? And we also know a corresponding x and y value in the first derivative. So we could say here that 2 times 2 plus c equals 5. So 4 plus c equals 5, so we know c equals 1. So we can now say that the first derivative is equal to 2x plus 1 because we are given a known coordinate of the first derivative. We can plug in that x and y value to find c. So now we know the value of the first derivative. Well, we know if we take the antiderivative of the first derivative, we're going to get the original function plus c. So here, we're going to take the antiderivative of 2x plus 1. Well, the antiderivative of 2x plus 1 is going to be 2 over 2 x squared plus 1 over 1 x to the first plus c. So we know at this point that our original function is equal to x squared plus x plus c. But we still have this c value. So now we're going to use the known coordinate point of 210 in the original function to find that c value. Okay, 10 is equal to 2 squared plus 2 plus c. So 10 is equal to 6 plus c. C is equal to 4. So we can say very clearly here that f of x is equal to x squared plus x plus 4 in this example. That would be your answer. Okay? So I would like you to do this next one on your own. Now, the last thing I'd like to talk about is the first application we can use anti-differentiation with. And that's when it comes to position, velocity, and acceleration. So here is a perfect example. A particle moves along the x-axis at a velocity of v of t is equal to 1 over the square root of t for t is greater than 0 at time t equals 1. Its position is 4. So remember, okay, we know that our position equation, s of t, all right, can be converted into the first derivative, which is velocity, which can then be converted into acceleration, which is the second derivative. So you can work backwards, okay, to find the starting position. So in this case, the antiderivative of velocity would be our position. The antiderivative of acceleration would be our velocity. Okay? So now we're going to be able to intertwine both differentiation and antidifferentiation. For example, here, part A asks, what is the acceleration of the particle when t equals 9? Well, here, velocity is going to be 1t to the negative 1/2. So we're going to find the first derivative to find acceleration, which in this case will be negative 1/2 t to the negative 3/2. All right? So then we just plug in 9 to find our acceleration, and we get negative 1 over 54. All right? Negative 1 over 54. All right. So here, for part B, it's asking you for the position of the particle when t equals 9. So remember that when we take the antiderivative of velocity, we're going to get position. So you're going to take the antiderivative of 1t to the negative 1/2. I'm going to go ahead and have you do this one on your own to find the position at t equals 9. Have a great day, everybody.